Hi! As we discussed in the previous lectures, we need to know about math or mathematics, physics, and also Python programming language in order to understand the quantum computers in a much better way. So that's what we're going to start with in this lecture. We're going to start with math, and we're particularly going to start with the probability. We're going to have to learn about probability and also statistics and also matrix as well. We're going to learn about mathematical formulas and also other stuff during these lectures. So I switched over to my iPad view. Right now you're not seeing the high definition presentation or the MacBook screen that I generally use. You're seeing the iPad view, so the pixelation may be a little bit worse, but bear with me, it's going to be temporary. But we need a pen in order to just let you know about some formulas and some kind of calculations. That's why I switched over to the iPad view, by the way. And we're going to start with the basics. We're going to start with the probability. Maybe you know all about this stuff, but believe me, it's going to get harder. So I really suggest you stick with me and just follow me along during these lectures. Okay, so let's find the related presentation, and here you go. So we are in the probability and binary logic. So if you see a term like this, P of A, it means that probability of A. So probability of A happening, like probability of me going out, for example, or probability of me being chased by a dragon. So it can be either 0 or 1. It can be either 0% or 100% or anything in between as well, obviously. So if you see the P, A and B, it means that both A and B happening at the same time. Or we can have some logical statements like A and B or C. Of course, it means that at the left hand side, A and B happening at the same time, or C happening on its own. So whether A and B happening or C happening. Or maybe they're both happening at the same time, but it's good to go with only one of them in this case. So I believe you know the difference between AND and OR. So AND means both of the equation, like the left hand side and the right hand side, should hold. And OR means the left hand side or the right hand side should hold in order for this to happen. So in this case, we can use logical expressions inside of a probability code like this in order to just define something happening and the probability of it. We're going to use this a lot during the quantum computations. So first of all, we need to understand how this works. So let's assign some exemplary situations for that kind of concept. For example, PA can be me going out for the night. PB is my wife going out for the night, and PC is the dog going out for the night on its own. So for example, the latest statement is the probability of me and my wife going out. Okay, we're going out, whether together or separately, or the dog is going out on its own. So what's the probability of that? It's that situation, it's that phrase. Okay, and can have some consequences, or we can have some other logics for that as well. For example, let me go to the next slide, and as you can see, if P, A and B is equal to 0, then it's called mutually exclusive. So if there is no way for me to go out and my wife to go out, for example, because somebody has to stay at home and watch the kid, then it's mutually exclusive. Okay, it cannot happen at the same time. Or we call some event independent. If they are independent from each other, they are not relevant at all. So maybe there is a babysitter at home, and whether me going out at the night or whether my wife going out at the night does not depend on each other. Maybe I'm going with my friends, Okay, maybe my wife is going with our friends and they are independent from each other. We don't depend each other. So it means that I can calculate the probability by multiplying me going out, the probability of me going out, and probability of my wife going out. Of course, at the mutually exclusive, it's always 0%, but if it's independent, then I can just multiply the possibilities together in order to find something happening at the same time. For example, if I have 30% of going out, or my wife has 50% of going out, so I can multiply 50% by 30% and just find all the possibility of these things happening together. Okay? But if we just change the statement to or, for example, then things change. Because remember what mutually exclusive is, PA or PB. So there is no way for us to going out at night together. So I have like maybe 30% of going out, and my wife has 50% chance of going out, but we cannot go at the same time. So me or my wife going out, not at the same time, but I wait at home, she goes out, or she waits at home and I go out, then I can just add those possibilities together to find whether she or me is going out at that night. The probability of that happening, one of those is happening. And if they're independent from each other, then it means that we need to subtract the A and B happening at the same time. Because if they're independent from each other, then it means that in the P of A and P of B, we already have P, A, and B, and we are counting it twice. Then we need to subtract P and B happening together, okay, if the event is independent. So whether an event is independent or mutually exclusive should be given to us if we want to calculate some kind of probability, or we can understand it intuitively when we read a paragraph or when we read the problem itself. Okay? So consider this scenario. P of A is 30% and P of B is 40%. So if somebody asks us to calculate P, A, or B, then we need to know if we're going to subtract the P, A, and B or not. Of course, in this case, they are independent and it's given to us with some kind of problem, with some kind of information. If that's the case, then I can just add 30% to 40%, which is 70%. But I also have to subtract P, A, and B happening at the same time. And remember, we need to just multiply all of those things together in order to calculate P, A, and B. And in that case, this is 0.12. If we subtract 0.12 from 0.7, then it means 0.58, which is 58% of chance this is happening, either A or B. Okay, and this is how we calculate the probabilities. In the quantum computation, we're not going to be dealing with exactly that kind of situation, but we're going to be dealing with the probabilities all the time. So I believe this is a good start for us in order to learn about math fundamentals for quantum computing.